Let's continue the discussion on this course on advanced reinforced concrete design. We are discussing the module 5, which is behavior and design under flexural loads. We are in the part 5. Previously, in the first four parts of this module, we discussed how to do moment curvature analysis, and we also discussed background to the flexural theory, and we derived for a single reinforced section, how the moment curvature behavior is going to change with increase in your reinforcement ratio. And then we looked at what is the effect of concrete compressive strength. Then later on, we moved on to see what is the effect of axial compression on the moment curvature behavior. Then we also talked about how putting compression steel is going to change the moment curvature behavior. Now, in this part of the module, we are going to completely focus on how to use IS code, Indian Standard Code of Practice, which is your IS 456 provisions for doing the design as well as doing the analysis. Okay, right. So the expected learning outcomes are going to be how to design for singly reinforced section using IS code provisions, and how to derive the limiting neutral axis depth and limiting moment of resistance using code specified provisions, including the design stress strain curves which are specified by the IS 456. Then we will move on to how to design doubly reinforced section. When you need doubly reinforced section, how do you do the design? Those things that we will discuss, and then we'll talk about how to analyze and design a flanged section. Right. So let's first see the first four parts of the module. What is the fundamental assumption we made? If you test a concrete cylinder, in fact, testing cylinder with an aspect ratio of more than 2 is actually going to give you the true material stress strain response of the concrete. So we use that, and for steel we use elastic perfectly plastic stress strain relationship. Okay, that is to understand the behavior. If we have these material properties, how the flexural behavior will change. But IS code as a design code, it wants the design engineers to calculate the capacities in a conservative way. We should not be overestimating the capacity. So the code is actually specifying design stress strain curves, which we will talk about. But again, the fundamental assumptions in your flexural design still remains the same. So whatever that we did, that is basically plane sections remain plane before and after bending, and the maximum strain in the concrete at the outermost compression fiber, that we are going to take that as 0.0035, which is what we have been using in your actual behavior also. When concrete at top reaches a strain of 0.0035 in compression, that means failure. And we are going to use not the parabolic stress strain curve that we are going to get from testing a cylinder, but we are going to test cubes. In fact, IS code specifies you to test cube. Anyway, we have a correlation between cylinder strength and cube strength, and we know that cube strength is going to be 25% higher than your cylinder strength. So that is what the code, because it's easy to cast and test. So this has been, we have been following it. So the code is recommending to test cubes after 28 days of for establishing the strength. Now, for the design purposes, we are going to use basically um, the compressive strength of the concrete. Actually, what we're going to use is, no, we're going to use a design stress strain curve, which is going to take 67% of the characteristic strength. Okay. And in top of that, we are also going to apply a factor of safety, which is a material safety factor, which is 1.5. Okay. We will see the stress strain curve. How is it going to be? Okay. Then the tensile strength of the concrete is ignored because we have seen it in the first parts of the module also. Tensile strength of concrete is only about 10% of the compressive strength. It's not going to really add much in terms of moment resistance, so it can be ignored. But however, it is not valid when you're using fiber reinforced concrete, especially with very high volumes of fibers, particularly steel fibers, right? And then for steel also, the stresses in the reinforcement can be derived from the design stress strain curve based on the type of steel. Okay. Again, design stress strain curve includes this factor of safety for steel, which is 1.15. Okay. So partial safety factor for material for steel is 1.15. We know that. This is a very important assumption, the last assumption. Okay. So the maximum strain in the tension reinforcement, that is the tension most reinforcement in the section at failure shall not be, in fact, it should not be shall be greater than. Okay. So it should be greater than this specified value. Okay. So this is very, very important. Okay. If you look at the first part, we looked at the yield strain as how the yield stress of the rebar divided by the elastic modulus. We just took that because we use elastic perfectly plastic behavior. But here the code is giving you a yield strength. So this is your definition for a yield strength. So this is nothing but your epsilon S Y as per IS code. So let's calculate what would be the value for your FE 500. So FE 500, it will be basically 0.002 plus, sorry, 0.002 plus 500 divided by 1.15 multiplied by 2 into 10 to the power of 5. So if you run the numbers, you are going to get yield strain for a 500 grade as 0.002 plus 500 divided by 1.15. Again, that is divided by 2 to the power of 5. It works out to be 0.00417. So this is your yield strain for a FP 500. Okay. So similarly, you can calculate a yield strain as per the IS code for different grades of steel. Okay. Higher the grade of steel, higher will be the yield strain. So this is the minimum strain that rebar should reach before the concrete at top reaches a compressive strain of 0.0035. So the code is going to make sure that the designers are going to reach at least this value. So now you can ask me, why is it so, right? So if you use the elastic perfectly plastic, we got a yield strain of 0.0025. So by having a higher value of yielding strain in your design, the code is making sure that absolutely the steel in the tension side is going to reach higher than your actual yield strain. So this is a slightly an amplified strain that the code is specifying to make sure that before concrete reaches compressive strain of 0.0035, steel is going to definitely yield. That is why the amount of reinforcement also will be controlled by that, which we will discuss in due course. Right. So now let's look at how the design stress strain curve for concrete is. Okay. So we have seen how was the previous curve that we have seen. So if you look at the stress in the concrete as let's say FC and epsilon C. So how was the previous curve that we have used? When you test your cylinder like this, you have seen in the material aspects. Okay. When you test a cylinder like this and you measure your 2 points and then you measure your strain between these 2 points, then you can plot your stress versus strain. Your actual cylinder stress strain curve will be like this. Go like this. Okay. So this is your actual stress strain curve parabolic model, especially for concrete strength less than 40 megapascal. And we know the correlations between your cylinder strength and cube strength. Then if you look at it, for a 40 megapascal concrete, for cylinder strength of 40 megapascal, actually characteristic strength here it will work out to be about 42.25 or so. Okay. So the code is saying, okay, if you are using characteristic curve, again, what is a characteristic curve? Is only 5% of the samples are expected to fail the specified value, right? So that means it is going to be much lesser than my mean strength. So FCK is actually mean strength minus 1.65 times your standard deviation. If you're talking about 30 megapascal standard deviation, we take about 5 megapascal. So it works out to be basically mean strength minus 8 megapascal. Or in other words, my mean strength for my material design should be characteristic strength plus 8 megapascal. So if I want 30 megapascal as a FCK, I should my mixed design strength mean strength should be having 38 megapascal, right? So we know all those things. So once we got your FCK, so the code is saying that okay, just for simplicity, because At the end of the day, what is the purpose? We want to make sure that we calculate the capacities in a reasonably accurate way, at the same time in a conservative way. So the code has actually specifying us to use a parabolic portion for strain up to 0.002. Okay, so you can see that this is a parabolic curve. So this is your actual curve. Okay, then what we do, this is a characteristic sum. Then we get your characteristic curve as 0.85 multiplied by zero point 0.8 FC. Again, why is that zero point 0.8 comes? Because we wanted to convert it into an actual material strength, which is your cylinder strength. Cylinder strength is 80% of your tube strength, so you multiply. And there is one more factor, 0.85, to account for the size. Okay, so because material test, you're doing it in a very small sample, but actual beams are quite large, the possibility of defects are going to be more. So the code is actually putting one more reduction factor of 0.85. So we discussed all these things in the material aspects, right? So that is why FCK is multiplied by zero point 0.8 and 0.85, that ends up with 0.67 FCK. That is your characteristic curve. Okay. So though you may define an FCK, again what we are doing, we are converting from cube to the cylinder strength, which is actual material property. In addition to that, we are also recognizing that the material tests are done in a small samples, but actually we are designing a large beams. Okay, so there the possibility of defects going to be high. So we are again multiplying by 0.85 to account for the size of it, right? So you end up with 0.67 FCK. And in addition to that, what the code is saying is, again you divide this by partial safety factor. So that's why the 0.67 is divided by 1.5, which is nothing but your gamma m for your concrete, which is 1.5. So 0.67 FCK divided by 1.5 gives me 0.447 FCK. So you can ask me, now if you look at concrete, first of all, it is not mean strength, we are using characteristic strength. Even in the characteristic strength, how much is the maximum stress that we are actually using it in our design? It's only about 44.7 percentage, 0.447 FCK. Roughly about 45 percentage of your characteristic strength is what we are assuming in our calculations. Anyway, this will not have a significant effect on your flexural capacities, because again the code is making sure that you're going to make the steel yielding before concrete reaches its compressive strength. Uh, this much reduction is also because when you're doing under reinforced section, it will not have a big change in your capacities, that we will see. We will get about 15% or so reduction than your actual material property. That comparison also we will see what we have done in the previous parts. Plus, if I use these stress strain curves, what are the value that we're going to get, that we're going to compare. Okay, so the design stress strain curve is the one that we are seeing here. So that is basically, if you look at, let's say, put that as a brown. So this is your design stress strain curve. It's going to be parabolic up to a strain of 0.002. Then it is going to remain a constant stress of 0.447 FCK for strain limit up to epsilon c. Again, the failure strain is when top compressive fiber strain reaches 0.0035, it is failure. So this is the design stress strain curve. So the equation for that is given us here, just like your parabolic model. So you can see that for any strain epsilon, I can calculate my stress FC. When epsilon is less than 0.002, it is basically your parabolic model. Okay, this is nothing but your parabolic model. Okay. This is nothing but your parabolic model. Only thing is, instead of f prime c previously used, we are using 0.447 FCK. And this parabolic relationship is again valid only when epsilon is less than 0.002. Again, what is the peak strain corresponding to your peak strength that you are calculating? It is actually 0.002. We have seen it in your material test also. For strength up to 40 megapascal, epsilon prime c that we have considered in the previous parts is going to be 0.002. It is not going to change much. So that's what the code is also using for peak strain 0.002. When epsilon becomes more than, if I'm taking strain, let's say at this point or this point or this point, the stress actually remains at 0.447. It is basically remains constant at 0.447 FCK. So design stress strain curve has two components. One is parabolic portion, and here also you can see it is also everywhere I have applied the partial safety factor 1.5. So the slope is also, so we have a parabolic portion that is valid up to strain of 0.002. Then there is a rectangular portion that is valid from strain of 0.002 to 0.035. Now, right? So this is the concrete stress strain curve, design stress strain curve that is specified by IS 456. Now this is valid for strength up to M55. Though some results are showing that this design stress strain curve is not really adequate, but if you are using other special concretes or very high performance concrete or high strength concrete, this design stress strain curve is actually will not be valid. You have to develop your own design curves based on your material testing. So that is why the focus of this course is basically focusing on fundamentals. Tomorrow, if you are given different stress strain curve also, using the fundamental principles, you should be able to calculate the capacity. So that is the whole idea. So you can keep this in mind. So the design stress strain curve can change from different codes also. Right now, the IS 456 is using this as a design stress strain curve, and it is shown to give you conservatively estimation of the capacities for normal size of beams and normal grades of concrete. Okay. Now, so this is the same stress strain curve we are going to use for your analysis. Okay. So again, if you look at this, okay. So this section that we are looking at, rectangular section that we are doing, singly reinforced section. Okay, like what we have it here, singly reinforced section. Okay, and what is that we are saying? We are doing analysis. Okay, and the top compressive strain at ultimate, I'm taking it as 0.0035. So basically, what is that we are doing? So we are, if you look at it, this stress strain curve, right? What we have used, we are basically rotating that by 90 degree, and this is going to act. For each strain, I know the stress. For example, when strain is 0.0035, the stress is 0.447 FCK. So that is what we have. So at this location, I'm going to have basically 0.447 FCK, right? So as you go along, then the stress will change in proportion to this. Or when you have strain at this point, for example, the stress FC, what is that I have to follow? I have to follow this relationship. Then because at this location, I know that epsilon C is less than 0.002, right? So you have to use the parabolic curve. Okay. So that is what the code is giving here. Now, as we have done previously, okay, the code is also giving you integrating all the compression force CC and giving you the value as 0.36 FCK XU. Now this stress, if you look at it, so if you see this as your cross section, and this stress is acting perpendicular to this cross section. Okay, if you take this as your cross section, this stress is acting perpendicular. So this force has to be multiplied by the width to get my total force. So that's why CC will become 0.36 FCK D into XC. So that is your concrete force in compression. So this is your stress block parameters. Stress block parameters C has to be multiplied by width for a rectangular section to get your CC, right? So this is the stress strain curve, design stress strain curve that we are going to use as per IS 456 2000. Okay, this may be changed in due course of updation of your course, but at this point of time, these are the specified design stress strain curve parameters, and we are going to use them. Okay, now what happens to steel? Again, if you look at steel, there are multiple grades are available, but commonly used is Fe 415, Fe 500, Fe 550, and now there are also Fe 550D is available, right? Now, in this case, I'm just showing the design stress strain curve for steel. Okay, so if you look at this case also, deformed bar stress strain curve, this is your characteristic curve. Okay, it will be like this. Okay, this is your characteristic curve. Okay, this is your characteristic curve. But this curve again is divided by gamma m, which is 1.15 for steel. Then you get this curve, which is your design stress strain curve. So, which is your this is your design stress strain. This is your design stress strain curve. This is your design curve for steel, right? So let's look at now how. Let me erase this for better clarity. So you see, you have the characteristic curve. Again, the characteristic curve is divided by the partial safety factor for steel. But in steel, we are dividing this characteristic curve only from zero point 0.8 or 0.87 Fi or only after this 0.8 FD stress, because anyway linear elastic portion, the quality of the steel is good, so the code is assuming the design curve and characteristic curve is same up to the stress level of 0.8 FYD, where FYD is basically 0.87 times Fy. Okay, so up to stress level of 0.8 FYD, there is no partial safety factor is applied. So the characteristic curve and design curves are going to be same. Only when the stresses are going to be higher than 0.8 FYD, then you have your partial safety factor is applied. Now, you can see here when you calculate your capacities, so we should know if it's a bilinear curve, you know exactly what it is, right? So this is the bilinear curve that we have used, if you remember in the first part, right? So it's pretty straightforward. Okay, so up to strain of your epsilon y, you know how to calculate. Basically, stress is elastic modulus times the strain. And the moment strain becomes more than epsilon y, then it is going to remain constant a value of Fy. So it's very easy to do the calculation, but the code is specifying this as a design stress strain curve. So this is what we have to use for calculating the capacities. Okay, so the code is giving you for design stress strain curve what are the values. For example, for a strain when total strain of 0.00174, the stress is 347.8. That corresponds to 0.8 FYD, where FYD is your the yield stress per design, which is taken as 0.87 Fy. So this stress 0.8 multiplied by 0.87 Fy is basically this. So this we are showing it for a stress of 500 megapascal, right? So if you look at it, then what would be your FID for that 0.87 Fi? For this is going to be 0.87 multiplied by 500. So 0.87 multiplied by 500 is basically 435. So it's going to be 435 for Fe 500. So FYD is this. But this is 0.8 times 435. So that is why it works out to be 347.8. Similarly, because this is a nonlinear curve, so the design stress strain curves are specified here. So for example, for a strain of 0.00195, you get a stress of 369.6, and then at a strain of about 0.00417, we get a stress of 434.8, which is your 435, the yield stress. Now you can tell me, so how did you get your yield strain? So this is how we specify, right? So what we do, we draw a parallel line at a strain of 0.002. So I take the same slope. This slope is basically your elastic modulus. Okay. So you take the same slope and then you draw like this, and then wherever it is going to touch this, that is going to be your yield stress. That yield stress we have defined that as 0.87 Fy. So what would be this total value strain corresponding to that? It is going to be basically this value plus this value will be your strain. So this is, we know that it is 0.002. And what would be this value? I know the stress is 0.87 Fy. That you divide by ES will give me the total value. So that's how when you add them, you get a value of 0.00417. So that is your strain, yield strain. So because for a deformed steel rebar, yielding is not very well pronounced, unlike your mild steel. So you have to take the 0.2 percentage strain and then draw a parallel line with the slope of elastic modulus, and wherever that is hitting, that is your design yield stress, that is going to be 0.87 Fy. So you can calculate the strain. So strain is going to be 0.002 plus 0.87 Fy by ES, which is 0.00417. So of course, with change in your grade of steel, this value is also going to change. Okay, this is the design stress strain curve that we are going to use. Similarly, you can also have design stress strain curves specified by S given for Fe415 and Fe250 also. Okay, but Fe250 there is no issue. So directly the values are specified. So for these values, whatever that are specified here are valid only for Fe 500 grade. Okay, so the only problem is when the strain is less than this value, which is 0.00174, then I can directly calculate my stress by multiplying with elastic modulus. But when the strain is between 0.00174 and 0.00417, I have to do interpolation using this design stress strain curve. So that is why these values are specified here, right? You see here? Yeah. So when your stress strain is somewhere here, then it is very easy. So stress is basically directly ES multiplied by epsilon S. Okay, but when you are in this region from here to here, we have to follow this table. Okay, and when your epsilon S becomes more than 0.00417, then the stress is going to be constant. What is that value? It is going to be 0.87 Fy, which is equal to 434.8 megapascal. Okay, so only when we are in this regime, we have to follow this table. So that means when the strain is greater than 0.00174 and less than 0.00417 for this grade, then we have to use this interpolation between these 6 points that are given there, right? So please keep this in mind, and we will also run an example to show this. Okay, now we are going to start how to analyze the singly reinforced sections. Okay, so first we will see, now that we have seen what is the design stress strain curve for concrete to be used, what is the design stress strain curve for steel to be used. Now let's take a simple singly reinforced section like the one that is shown here. Okay, again, what is singly reinforced section? You have reinforcement only on the one side, which is the tension side, and this is the typical section that we take with B and D as overall depth, and small d is your effective depth. Okay, now we are showing only the ultimate conditions. Okay, so for example, this is your balanced condition. Again, what is the definition for your balanced condition? Concrete should reach a strain of 0.0035 and steel should reach a strain of yield strain, design yield strain. Okay, at simultaneously. Okay, now what is the design yield strain for IS 456? We have seen for Fe4 for any grade of steel, it is going to be 0.002 plus 0.87 Fy by ES. Okay, so this is your strain. So for Fe 500, we calculated that to be 0.00407. So I fixed this limit and I fixed this limit. This is basically epsilon Cu. So that is always fixed. Okay, and this is your balance condition. So for this condition, if I know the effective depth, I know I am fixing these two strains, right? So basically this distance is known, and now what would be this distance? Again, we have done this calculation, right? Is going to be d minus xu max, right? So the strain levels are fixed. The moment I am saying that the section is a balanced section, then my strain values are fixed. So why are we doing this is, in a section, I put reinforcement, only so much reinforcement I can put so that the strain in the steel when it is failing should at least reach this strain. So this is the maximum, the XU max that I can allow in my flexure design if I'm following IS 456 provision. So I want to calculate, I always want to make sure that the section is designed like this. I put the amount of reinforcement in such a way that this XU should always be less than XU max. So that when this value is fixed, okay, when X becomes less than this, then this strain, okay, epsilon ST will become more than epsilon STY, which is your tension value. This is this. Okay. So that is our intention. So we want to make sure that the strain on the tension side is going to be greater than your design yield strain specified by your IS 456. Okay, so which is 0.00407 for your Fe 500 grade of steel. So this is your under info section. So in a section, I can put maximum amount of reinforcement that will lead to maximum value of Xc max. This is the maximum that is allowed by the code. Okay. So for this, basically, this is a balanced section that we are calculating. Okay. So let's calculate now Xu max. Okay. For all sections, if I put steel less than corresponding to the balanced reinforcement ratio, the steel is always going to exceed the yield strain, design yield strain that are specified in your IS 4. Now we'll focus only on this, okay, and then derive what is the expression for your Xc max. Okay, so let's not worry about this. Okay, for now let's focus on this. Okay, so let us see now what happens from strain distributions. We know from similar triangle we have done that. Okay, so I want to find the value for your Xc max. Okay, so from strain distribution, so we know 0.00 from similar triangle 0.0035 by Xc max should be equal to this value divided by this distance. Again, we know this distance, right, is going to be d minus Xu max. Okay, so if you readjust these things, we can find an expression for your Xu max by Bt as this. Okay, or in other words, in a simpler way, we can also do like this. Okay, so if I keep shifting this location, the strain, okay, this slope, if I, by keeping the same slope, if I change this line, okay, to start from here, so what would happen? So this value would have, this value would be basically nothing but your, it would have shifted by same value 0.0035. So that is what we get here. Okay, so 0.0035 plus 0.002 will become 0.0055 plus 0.87 f5. Okay, so in this way we can also simplify and we can find out an expression for your Xc max by d. Okay, but anyway, so this is a simple similar triangle. So using that, I can find an expression for my Xc max by d as 0.0035 divided by 0.87f5 by s plus 0.0055. Again, how did we get this 0.0055? Is what I said. When you shift this, okay, then you can find that, right? So this is the expression. Now this is your Xu max by d, the maximum neutral axis depth that section is allowed to have. And so that when concrete reaches a strain of 0.003, at least the steel should reach its minimum yield specified by the code. If it is not yielding, that amount of reinforcement is not allowed as per the code. Okay, so that is why this is the maximum neutral axis depth a particular section can take, so that it can ensure just yielding of your steel. Okay, that is that also not your this is your yield strain, design yield strain specified by your IS 456, which is your this value, which is 0.002 plus 0.87 fy by es, right? Okay, so we can see that from this expression, of course, we can find out what is Xc max by d for different grades of steel. Okay, now in this equation, concrete strength doesn't come at all. Okay, because this is a failure condition which is defined only based on strain condition. That means I'm fixing my Xu max, and then I'm fixing my strain at the bottom, and the yield strain is only function of your grade of steel. It has nothing to do with your concrete grade. So that is the reason Xc max by D is only function of your grade of steel. It has nothing to do what grade of concrete that you're using in your section, because it is defined by strain conditions for for concrete strain at failure for any grade of concrete up to 40, or as per IS 456 up to M55, we use only 0.0035. So it's not going to change, right? Similarly, the yield strain is function of only the grade of steel. So when you plug in for a Fi, then you can get different values for your Xu max by D. Okay, so you can see that it is basically it is reducing Xu max by D values, reducing as your grade of steel is increasing. Okay, so why is it so? Because again, we can see that when your grade of steel is increasing, my yield strain also is going to increase. So when yield strain is increasing, when your top compressive fiber strain is fixed, then your Xc max by D also has to come down. Okay, so that is what we are saying.